Imagine scientists confirm tomorrow that something is already coming through the ice. Not a signal, not a theory, a chemical signature, frozen into the surface of Europa. Carbon dioxide, locked into the chaos terrain of a region called Terra Regio. 2 independent research teams, 1 instrument, the same result. The carbon did not fall from space. Every team that looked at the data ruled that out. It came from below, from a body of liquid water sitting behind 15 to 25 miles of ice. An ocean holding more total volume than every ocean on Earth combined. An ocean that has been continuously liquid, in complete darkness, heated by Jupiter's gravity for 4 billion years. James Webb Space Telescope made this observation on September 21st, 2023. 2 papers. Journal Science, same data set, same conclusion. The carbon is there, the ocean is the source. Tonight we go through what Webb actually detected and how the instrument reads chemistry from 390 million miles. What Terra Regio reveals about the structure of the ice and what is below it. What a chemically active ocean-moving material toward the surface implies about what might be inside it. And why the scientists who published these findings chose their words with unusual care. Subscribe now if you want the version that does not stop at the headline. We begin. The image you have of Webb is probably the same one everyone has. A gold hexagonal mirror, deep field photographs, galaxies 10 billion light-years away, resolving into spirals that look like pinwheels. Telescopes take pictures. That picture of what Webb does is not wrong. It is incomplete. The instrument that found carbon on Europa is not a camera. It is called NIR-SPEC, the near-infrared spectrograph. And what it does is not photograph a surface. It reads the surface's chemistry from a distance so large it is almost impossible to make concrete. A telescope cannot see what is under the ice, but it can read what the ice is made of. NIR-SPEC operates in a wavelength range called the near-infrared, from roughly 0.6 to 5.3 microns. Human vision operates between about 0.4 and 0.7 microns. NIR-SPEC sees well past the edge of human vision, into the infrared region where the vibrational signatures of molecules are strongest and most distinctive. Carbon dioxide has a particularly strong absorption feature near 4.26 microns, a doublet of 2 closely spaced dips produced by 2 different vibrational modes of the molecule. Detecting both dips at the predicted wavelengths for carbon dioxide is far more diagnostically certain than detecting a single feature would be. Both were present. NIR-SPEC was used in a specific observing mode called the integral field unit, or IFU. A standard spectrograph points at one location and returns one spectrum. NIR-SPEC's IFU divides a patch of sky into a grid of spatial positions and records a full spectrum from every position simultaneously in a single exposure. When aimed at Europa, this produced not one spectrum of the whole moon, but a grid of spectra, one from each patch of the moon's disk, all taken at the same time under identical observing conditions. This spatial sampling changed what was detectable. If NIR-SPEC had been a standard point spectrograph, it would have returned one average spectrum of the entire moon. The carbon dioxide signal from Terra Regio, blended into the much larger average signal from the rest of the surface, might have been diluted below the detection threshold. The IFU preserved the spatial contrast. The pixels over Terra Regio showed the carbon dioxide doublet clearly. The pixels over older terrain elsewhere showed it weakly or not at all. That contrast, as much as the detection itself, is what makes the conclusion about internal sourcing scientifically compelling. External sources produce uniform distributions. Internal sources produce localized ones. The NIR-SPEC instrument's sensitivity is worth quantifying. Webb's primary mirror is 21 feet across, a hexagonal array of 18 gold-coated beryllium segments, that collect and focus more light than any space telescope ever built. The gold coating is not decorative. Gold reflects near-infrared wavelengths more efficiently than any other material, maximizing the amount of infrared light that reaches the spectrograph. The detector arrays behind a near-spec are cooled to -233 degrees Celsius, within a few degrees of absolute zero, to minimize the thermal noise that would otherwise swamp the faint infrared signals from distant objects. All of this engineering exists to detect signal at the level where the carbon dioxide doublet appears in Europa's spectrum. Before Webb, the best infrared spectroscopy of Europa from space was performed by Galileo's near-infrared mapping spectrometer, NIMS, which operated from 1995 to 2003. NIMS covered wavelengths from 0.7 to 5.2 microns, overlapping with the NR-spec's range. But NIMS operated from a spacecraft in orbit around Jupiter, not from a large space telescope with a 21-foot mirror and cryogenically cooled detectors. Its spectral resolution and sensitivity were a fraction of what NR-spec achieves. NIMS found evidence of hydrated salts and possibly carbon dioxide on Europa's surface, but the signals were ambiguous and their interpretation was contested for years. NR-spec settled the carbon dioxide question with the first unambiguous detection at the spatial and spectral resolution needed to distinguish Terra Regio from the surrounding terrain. The Hubble Space Telescope had also observed Europa multiple times before Webb. Hubble operates primarily in ultraviolet and visible wavelengths rather than the infrared. Its contribution to Europa science was the tentative plume detections and the salt signatures in the chaos terrain, not direct carbon dioxide detection. The tools to make the near-spec detection existed only after Webb launched in December 2021, entered its L2 orbit in January 2022, and completed its commissioning by July 2022. The Europa observation came in the first year of Webb's science operations. Carbon dioxide on Europa was one of the early results from the most powerful infrared telescope humanity has ever built, targeted at a moon whose ocean scientists had been discussing for decades. 2 independent teams analysed this spatial dataset using different methodologies. Trumbo's team at Cornell University used spectral decomposition, fitting the observed spectrum at each IFU position to a linear combination of reference spectra for known compounds. The best fit to the Terra Regio pixels required a carbon dioxide component that was not needed for older terrain. Villanueva's team at NASA Goddard used radiative transfer modelling, computing what the spectrum should look like given specific surface compositions, and adjusting until the model matched the observed data. Different methods, same data set, same conclusion. The editors of Science published both papers in the same issue on September 21, 2023. Here is how. Light from the Sun travels outward in all directions. Some of it reaches Europa, 390 million miles away, and reflects off the surface. Some of that reflected light travels back toward us. Near-spec intercepts it and splits it, not into colours the way a prism splits visible light, into wavelengths across the entire near-infrared range, and every molecule in the universe, water, oxygen, methane, carbon dioxide, absorbs a specific set of wavelengths when light passes through it or bounces off it. The absorption pattern is like a fingerprint. Carbon dioxide has a doublet, 2 closely spaced dips in the spectrum, near 4.26 microns. No other molecule produces the same signature in the same place. When NIRSpec looked at Europa, that doublet was there. Clear, unambiguous, in Terra Regio specifically. Now make the distance concrete. Light from the Sun takes 8 minutes to reach Earth. Europa was 390 million miles from Earth when Webb observed it. The light NIRSpec analysed had been travelling for 35 minutes before it reached the telescope's mirror. In those 35 minutes crossing an empty ocean of space, It carried the chemical record of what it had touched on Europa's surface with enough fidelity for a spectrograph to read the absorption signature of a specific molecule from a world the size of our moon. NIRSpec's field of view on Europa was 10 pixels across the disk, not 10 megapixels, 10 pixels. Each pixel covered hundreds of miles of surface. What it returned was not an image, it was a grid of spectra, one spectrum per pixel, a spatial chemical map of what each region of the surface was made of, all captured simultaneously using the integral field unit, the IFU mode that records full spectral information at every spatial position at once. The carbon dioxide doublet appeared in the pixels over Tara Regio. It was weak or absent in the pixels over the older terrain elsewhere on the moon. That spatial contrast is the entire finding, not just that carbon dioxide exists on Europa, that it is concentrated in one specific place, and that specific place is not random. It is the place where everything the models say about the ice shell predicts internal chemistry should reach the surface. Samantha Trumbo's team at Cornell and Geronimo Villanueva's team at NASA Goddard analysed the same data independently. Different methodologies, same result. Published in Science on the same day, September 21st, 2023. When two independent groups reach the same conclusion from the same data using different methods, the scientific community treats the finding as solid. This one is solid. But the finding only becomes significant when you understand what Tara Regio actually is, because the location is not incidental to the result. The location is the result. If the ocean beneath Europa were leaking carbon upward through the ice shell, you would expect the signal to show up everywhere. The ocean is global. The shell sits above it everywhere. If chemistry is crossing from ocean to surface, why concentrate in one region? The answer is that the ice is not the same everywhere, and the difference is geological age. Europa's surface is unusually young for a world its age. Impact craters accumulate over time on any solid surface in the solar system. Europa has very few. The surface is being continuously refreshed by geological activity from below, but it is not refreshed uniformly. Some regions are older. Some are much newer. Tara Regio is new. It is what planetary scientists call chaos terrain. The name is not casual. The ice in this region is broken, fractured into tilted blocks that have partially refrozen in disrupted positions, the way sea ice looks after something large has pushed through it from below. Galileo spacecraft images from the late 1990s showed the texture clearly. Blocks of ice that were once flat now tilted, cracks between them, new ice refrozen in the gaps. The surface is chaotic because something disrupted it, recently. The carbon did not fall from space, it came from underneath. Here is why the geological age of the terrain matters for the carbon dioxide signal. Jupiter's particle belts continuously bombard Europa's surface with high-energy electrons and protons. This radiation is a chemical destroyer. It breaks apart complex molecules. It drives carbon compounds into different chemical forms over time. Old terrain, exposed to this radiation environment for hundreds of millions of years, has had its original surface chemistry modified, degraded, altered. Whatever arrived on old terrain long ago has been processed into something else. Young terrain is fresh. It has been exposed to radiation for far less time. The chemistry of what recently arrived from below is still intact, still readable. Carbon dioxide in old terrain would have been broken down by now. Carbon dioxide in new chaos terrain is still there because it arrived recently. Finding the carbon dioxide signal concentrated in the young terrain and weak or absent in the old terrain is the opposite of what external sourcing would produce. A comet impact or material from Io, the volcanic moon whose sulfur compounds colour parts of Europa's surface, would deposit material across old and young terrain alike. The radiation environment would then process it over time, leaving more chemical output in older terrain, less in younger. The pattern Webb found is the reverse. Internal sources come up through the weak spots, through the recently disrupted ice, through the chaos terrain, through Tara Regio. Hubble had already found something here before Webb looked. Ultraviolet observations of Europa had detected signatures consistent with ocean-derived salt concentrated in the chaos terrain regions, not just Tara Regio, but Tara Regio prominently. Sodium and magnesium compounds consistent with brine that had reached the surface and left its dissolved minerals behind. The salt was a first suggestion that this disrupted terrain was a place where the ocean and the surface were communicating. The chaos terrain of Tara Regio sits in the leading hemisphere of Europa, the side that faces forward as the Moon orbits Jupiter. This orientation matters because it is the face that sweeps up material from the Jovian system as Europa moves through its orbit. Some of the reddish-brown coloration across Europa's surface comes from sulfur compounds delivered from Io, the volcanic moon whose eruptions spray material throughout the inner Jovian system. The leading hemisphere accumulates this material most efficiently. Tara Regio sits in a region where external inputs from the Jovian environment and internal inputs from the ocean below are both active. Distinguishing between them requires exactly the kind of spatial chemical mapping that NIRSpec's IFU provided. The pre-Webb history of Tara Regio includes one earlier significant finding. Galileo's near-infrared mapping spectrometer had detected an infrared signature in some chaos terrain regions that some researchers interpreted as consistent with hydrated sulfate salts, compounds that could form if ocean brine reached the surface and underwent radiation processing. The signal was ambiguous, and the interpretation was contested. Hubble's later ultraviolet observations were cleaner in showing a chemical character in Tara Regio that was different from the rest of the surface. The Webb observation is the first with the spectral resolution and sensitivity to identify a specific carbon-bearing compound unambiguously and map its spatial distribution across the Moon's disk. The Galileo spacecraft's close flybys of Europa in the late 1990s and early 2000s produced the first high-resolution images of Tara Regio and the surrounding chaos terrain regions. The images from 1998 and 1999 are the clearest pictures of Europa's chaos terrain available before any follow-on mission. They show the tilted blocks, the refrozen matrix between them, the linear ridges crossing the terrain in different directions from different tectonic episodes. The surface has a geological complexity that demands an active interior. Static, cold, dead ice does not produce this texture. This texture requires ongoing exchange between the ice shell and something below it. Tara Regio's chaos terrain covers roughly 200 kilometers by 400 kilometers of Europa's surface, an area larger than France. It is not a small, isolated disruption. It is a major feature of the Moon's leading hemisphere, and its extent suggests that the convective upwelling that created it was not a local anomaly, but a regional or global process operating over a substantial area. The carbon dioxide that Webb detected is concentrated within this region. The spatial correlation between the young, disrupted chaos terrain and the carbon dioxide signal is not approximate. It is the same region. Europa's surface age in different regions is estimated using impact crater density as a proxy for time. More craters means more time has passed since the surface was last geologically reset. Europa's globally young surface, relative to other heavily cratered moons of the outer solar system, tells scientists that geological processes are actively erasing craters by resurfacing the Moon. Tara Regio, with among the lowest crater densities on the surface, was resurfaced most recently. The chaos terrain event that disrupted the ice and delivered the ocean-derived chemistry to the surface happened within the last tens of millions of years. On a moon whose ocean has been running for 4 billion years, tens of millions of years ago is recent. The surface is still fresh. The chemistry is still intact. Webb found it in time. The geological age of Tara Regio itself is estimated from the impact crater count in the region. Young terrain has few craters because its surface has been recently refreshed, and old craters have been erased. Tara Regio is among the least cratered regions on Europa, making it one of the youngest. The chaos terrain was disrupted, refrozen, and its surface chemistry reset relatively recently in geological terms. Recent here means tens of millions of years, not billions. Tens of millions of years is recent on a moon whose ocean has been running for 4 billion. The carbon dioxide Webb found has been sitting in the young, freshly disrupted surface ice of Tara Regio for a geologically brief time before the radiation environment could fully process it. That is why it is still readable. Webb confirmed something in the same family but a different order of magnitude, not just salt, carbon. The publication on September 21st, 2023, was itself unusual. 2 papers, same issue of Science, same data set. Trumbo's team at Cornell used spectral decomposition, fitting the observed spectrum to combinations of reference spectra until the best fit required a carbon dioxide component that was not needed for older terrain. Villanueva's team at Goddard used radiative transfer modelling, calculating what the spectrum should look like given specific surface compositions, and adjusting until the model matched the data. Both approaches converged, both published. The editors placed them side by side in the same journal issue so readers could compare the independent analyses. When that happens, the community takes the findings seriously. The carbon is there, the pattern is internal, and understanding how anything gets through 15 to 25 miles of frozen ice requires understanding what that ice actually is, which is not what most people think. 15 miles of ice, 25 miles of ice. Most people hear those numbers and picture a vault, a sealed container. Whatever is inside the ocean stays inside. Whatever is outside stays outside. The ice is the barrier. Nothing crosses. This picture is wrong. Not slightly wrong, structurally wrong. Ice at different temperatures behaves like completely different materials. The outer few miles of Europa's ice shell, in direct contact with the cold of the outer solar system at temperatures around minus 260 degrees Fahrenheit, is rigid and brittle. It fractures rather than flows. This layer is called the conductive lid. Heat moves through it slowly, by conduction the way heat moves through a stone wall. 15 miles of ice sounds like a sealed vault. The physics says it is more like a slow conveyor belt. Below the conductive lid, the ice warms. Closer to the ocean, the ice is continuously heated from below, by the ocean's warmth and by the tidal energy that Jupiter's gravity deposits into Europa's interior. Warm ice has lower viscosity. It deforms rather than fractures. It flows, over geological time, the way glaciers on Earth flow toward the sea. And warmer, less dense ice in a shell of colder, denser ice does exactly what warmer, less dense material always does. It rises. Convection. The same process that drives ocean currents on Earth. That moves tectonic plates. That produces the convective cells visible as granules on the surface of the Sun. In Europa's ice shell, warm plumes of ice deep in the shell are less dense than the colder ice above them. They rise. Cooler, denser ice above descends to replace them. The process is slow by human standards. Models built by different research groups using different assumptions about ice viscosity and the rate of tidal heating in the shell produce overturn timescales ranging from roughly 100,000 to 500,000 years per complete cycle. One complete overturn takes approximately as long as has passed since modern Homo sapiens first appeared on Earth. By geological standards, this is fast. In 4 billion years, the ice shell has overturned thousands of times. Each overturned cycle carries material from the base of the shell, where ice is in direct contact with the liquid ocean, upward toward the surface. The ocean continuously freezes new ice onto the base of the shell as the shell loses heat upward. That new ice, forming at the ocean boundary, incorporates whatever is dissolved in the ocean water at that interface. Carbon dioxide, salts, whatever organic compounds may be present. The ocean's chemistry is continuously loaded into the base of the shell and continuously transported upward. The chaos terrain at the surface is the surface record of where that upward transport has been most vigorous and most recent, where a warm convective plume reached the base of the rigid conductive lid and pushed hard enough to fracture it, where the rigid surface ice broke into tilted blocks on the softer ice beneath, where the plume eventually subsided and the surface refroze in its disrupted configuration. Galileo photographed the result. Webb read the chemical cargo, the same process that drives ocean currents on Earth. That moves tectonic plates. That produces the convective cells visible on the surface of the Sun. In Europa's ice shell, warm plumes of ice rise from deep in the shell toward the surface, while cooler ice sinks to replace them. The overturned timescale, the time for one complete cycle, falls somewhere between 100,000 and 500,000 years, according to models built by different research groups using different assumptions about ice viscosity and tidal heating rates. In 4 billion years, the shell has overturned thousands of times. Each cycle does something specific. It carries material upward. The base of the ice shell is in direct contact with the liquid ocean below. Ocean water freezes onto the base of the shell continuously as the shell loses heat to the cold ice above. That new ice forming at the ocean ice boundary incorporates whatever is dissolved in the ocean water at that moment. Carbon dioxide, salts, organic molecules if any exist. The ocean delivers its chemistry to the base of the shell simply by being there, and the convecting shell carries that chemistry upward, slowly, over geological time, toward the rigid lid above. When a warm convective plume reaches the base of the rigid conductive lid, it pushes. The rigid lid above it fractures under the mechanical stress. Blocks of surface ice tilt and shift on the softer ice beneath. Eventually the plume subsides. The surface refreezes in its disrupted configuration. The chaos terrain is preserved, a record of what came up from below, frozen into the surface for any instrument sensitive enough to read it. Webb was sensitive enough. The basketball model makes the scale concrete. If Jupiter were a basketball 24 centimeters across, Europa would be a marble sitting roughly 1.3 meters away. And on that marble, the ice shell that NIRSpec read through from 390 million miles is a coating thinner than the paint on the marble surface, proportionally speaking. The ocean below the shell is the marble itself. Inside that marble, in the dark, with heat from below, the chemistry that Webb detected in a marble-thin coating of ice has been running for 4 billion years. The conveyor belt analogy is precise because it captures the continuous nature of the process. A conveyor belt does not deliver one batch of material and stop. It runs continuously. New material arrives at the base. Old material reaches the surface. The cycle repeats. Europa's ice shell has been running this cycle continuously for as long as the ocean has existed. Carbon dioxide dissolved in the ocean 4 billion years ago has been carried to the surface and degraded. Carbon dioxide dissolved in the ocean today is being incorporated into new ice at the base of the shell and beginning its 100,000 to 500,000 year transit upward. What Webb detected in September 2023 is the most recent batch in a delivery that has been running since before Earth had complex life. The carbon dioxide that NIRSpec detected in Tara Regio is the chemical cargo of a convective event. Ocean chemistry, incorporated into ice at the base of the shell, transported upward over geological time, deposited at the surface when the convecting plume disrupted the rigid lid. The ice shell is not a sealed barrier. It is a chemically active, mechanically dynamic medium that has been continuously moving material from the ocean toward the surface for billions of years. Now consider what the ice has been moving. Because carbon is not just another molecule in this context. Carbon changes everything about the question. 6 elements. That is the list. Carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, chnops. Every living thing that has ever been found on Earth, in every environment, from boiling hydrothermal vents to the frozen cores of glaciers to the most irradiated soils on the planet's surface, runs on these 6. All of them, without exception. Carbon is first on the list for a reason that goes to the molecular architecture of life itself. The carbon atom can bond to 4 other atoms simultaneously, including other carbon atoms, forming chains and rings of arbitrary length and complexity. Amino acids are carbon chains. The proteins that catalyze every chemical reaction in your body are built on carbon skeletons. The sugars that power your metabolism are carbon rings. The fats that form your cell membranes are long carbon chains. DNA itself is a carbon backbone with bases hanging off it. The molecule that carries every instruction your body has ever executed is a carbon molecule. No other element does this with the same flexibility and stability in the temperature range where liquid water exists. Carbon in a liquid ocean 4 billion years old is not a coincidence waiting to be explained. It is a condition. Trumbo's language in the published paper was deliberate. She said carbon is a biologically essential element. Not that it suggests biology, not that it improves the odds, that it is essential, required, a non-negotiable ingredient, and Webb found it in the ocean chemistry of Europa, confirmed by its surface signature in the chaos terrain that the ocean communicates through. Now build the stack. Liquid water. Confirmed. Galileo's magnetometer detected the electromagnetic signature of a conducting layer beneath the ice in the late 1990s. The signature requires a salty liquid medium. An ocean. Global. Confirmed. Energy. Confirmed. Jupiter's gravity continuously flexes Europa's interior as the Moon orbits. The gravitational force varies slightly across each 85-hour orbit, squeezing and releasing the interior. That mechanical energy becomes heat. It keeps the ocean liquid at 390 million miles from the Sun, at a distance where, without that internal heat, everything would be frozen solid. Carbon? Confirmed. September 23rd, 2023. 2 teams, 1 journal, same finding. Step back and read what that stack means without softening it. This is not a world where liquid water exists and nothing else. This is a world where liquid water is confirmed, chemical energy is confirmed, and carbon, the primary structural element of all known biology, is confirmed in the ocean chemistry. These 3 conditions together define what the astrobiology community calls a potentially habitable environment. Europa is not potentially habitable in the theoretical, speculative sense that a world in the habitable zone of a distant star might be. It is potentially habitable in the empirical sense. The conditions have been measured. They are there. The Cassini mission to Enceladus confirmed that a second ocean world in our solar system has liquid water, chemical energy from hydrothermal vents, and a carbon-bearing ocean. Enceladus and Europa now represent 2 independent confirmations that ocean worlds in the outer solar system have the basic ingredients for life. 2 worlds, 2 oceans, 2 confirmations. The sample is growing. The question is whether the ingredient list has been used. Whether carbon in liquid water with available energy and geological time produces biology, or whether it just produces complex, interesting, sterile chemistry. Webb added the carbon data point. Everything else required to move from the ingredient list to the biology question is what Clipper is designed to address. 3 of the 5 core conditions that define a potentially habitable environment are confirmed. The question is not whether the ingredients are available. They are. The question is what those ingredients have been doing for 4 billion years of continuous operation in the dark behind 15 miles of ice. The remaining 2 conditions from the Schnapps list, nitrogen, phosphorus, and sulfur specifically, are not yet confirmed in Europa's ocean, but are strongly expected from the geological processing of the rocky silicate core. Nitrogen is abundant throughout the solar system in various forms. Phosphorus is present in all rocky bodies that formed from the same primordial material as Earth. Sulfur is confirmed in the Jovian system from Eo's volcanic activity and is present in the surface chemistry of Europa itself. The geological plausibility of all 6 CH-NOPS elements being present in Europa's ocean is high. Webb confirmed the most important one. What the conformation of carbon does not establish is the concentration. Life requires carbon in usable forms, not just present in any concentration. Dissolved carbon dioxide in ocean water is a usable carbon source for chemotrophic organisms. Methanogens specifically use dissolved carbon dioxide directly in their primary metabolic reaction, combining it with molecular hydrogen to produce methane. The carbon that Webb detected in Terra Regio, having been transported from the ocean through the ice, represents the carbon that was dissolved in the ocean water at the base of the ice shell when that ice formed. Its presence in detectable quantities at the surface, after hundreds of thousands of years of upward convective transport, implies that the ocean below contains dissolved carbon dioxide in quantities sufficient to load the ice measurably during freezing. That is not a trivial implication. The concentration of dissolved carbon dioxide in the ocean, constrained indirectly by what NIRSPEC detected at the surface, falls in a range consistent with what origin of life researchers consider favourable for the methanogenesis reaction. Not confirmed. Consistent. The carbon is there, in usable form. In an ocean that has had the energy in the liquid water to use it for 4 billion years. The question is whether 4 billion years was long enough. The N1 problem sits at the centre of why this question is so difficult to answer from the outside. We have exactly one confirmed example of life in the universe, Earth. Every theory about where else life exists, every estimate of how common it is, every prediction about what conditions are sufficient for its origin is derived from a sample of 1. You cannot do statistics with a sample of 1. You cannot distinguish between life being an inevitable outcome of chemistry given the right inputs, and life being an extraordinarily improbable event that happened once in 13.8 billion years of cosmic history. Europa is the opportunity to add to the sample, not to the sample of intelligent life, or complex life, or even multicellular life, to the sample of any biology at all. A second independent origin of life, anywhere, under any conditions, moves the statistical framework from hopeless to tractable. 2 examples tells you the process runs. 1 example tells you only that it ran once. Getting at that question requires understanding what 4 billion years of that kind of chemistry actually looks like. And the most important place to start is not with the chemistry. It is with the heat. Picture Europa's ocean as a physical place. Dark. Completely, permanently. No photon of sunlight has ever reached this water. The ice shell above blocks everything. Europa sits 390 million miles from the sun, and the sun's light at that distance delivers roughly 4% of what reaches Earth's surface. None of it penetrates the ice. The ocean has been in total darkness since the first day it existed. Cold at the top. The base of the ice shell keeps the upper ocean near freezing, but the temperature rises as you descend. At the seafloor, where the ocean contacts the rocky core, it is warmer. The tidal heating from Jupiter, combined with the decay of radioactive elements in the rocky interior, concentrates heat at the base of the ocean. This thermal gradient, hot floor to cold ceiling, drives circulation. It drives chemistry. Pressurized beyond any environment on Earth, the ocean is estimated to be between 60 and 150 kilometers deep. At 100 kilometers of depth, the water column above produces pressure that compresses the chemistry of the deep sea vents into different forms than they take anywhere near a surface. Salty. The electromagnetic signature Galileo detected requires dissolved ions, salts. The ocean is briny, more similar to Earth's seas than to pure water, accumulated from billions of years of rock-water chemical interaction. Life on Earth had to wait for oceans to form. Europa's ocean was ready before Earth's was. Earth's oceans date to approximately 4.4 billion years ago. Europa's ocean is believed to have been continuously liquid for a comparable period. But the early Earth's surface was a catastrophe of asteroid bombardment, volcanic outgassing, and temperature extremes. Europa's ocean, insulated beneath its ice shell, maintained by tidal heating, may have been a more stable chemical environment than early Earth's surface during that same period. To feel the 4 billion years instead of just reading it, the SR-71 Blackbird, the fastest air-breathing aircraft ever built, cruises at 2,193 miles per hour. Earth's orbital velocity around the Sun is 66,600 miles per hour, 30 times faster than the fastest jet. Jupiter's orbital velocity is slower, 29,000 miles per hour, but it is moving constantly through a solar system that itself moves at 490,000 miles per hour around the center of the Milky Way. Europa moves with Jupiter, orbiting Jupiter at about 49,000 miles per hour, orbiting the Milky Way at 490,000 miles per hour, at 390 million miles from a star that in the context of the galaxy is just another point of light. This ocean exists in motion we cannot feel, carrying chemistry we detected with a telescope, for a duration that resists intuition. The duration inversion applied to Europa's tidal heating makes the numbers tangible in a different way. Jupiter's gravity deposits tidal energy into Europa's interior every 85-hour orbit. That is roughly 3.5 orbits per Earth week. In 4 billion years, Europa has completed approximately 40 billion orbits of Jupiter, 40 billion tidal heating cycles, each cycle flexing the interior, each cycle depositing heat at the seafloor, each cycle keeping the ocean liquid. If you could watch 1 second of footage per billion tidal cycles, watching all 40 billion cycles would take 40 seconds. In those 40 seconds, from the ocean's first day to the day Webb looked at it, every living thing that has ever existed on Earth was born and died. When Europa's ocean was 1 billion years old, the first complex cells with nuclei were only just appearing on Earth. When it was 2 billion years old, Earth's atmosphere was still being built by photosynthetic bacteria. When it was 3 billion years old, the Cambrian explosion of complex animal life was 1 billion years in the future. When it was 3.5 billion years old, the most recent common ancestor of every living thing on Earth today had not yet appeared. The ocean has been running through all of it, in the dark, with heat from below, with minerals continuously dissolving from the rocky seafloor into the overlying ocean, with tidal heating from Jupiter flexing the interior 85 times per Earth week, every week, for 4 billion years. The energy input from tidal heating alone is substantial. Models of Europa's interior heat budget estimate that tidal heating delivers somewhere between 0.02 and 0.1 watts per square meter to the Moon's interior. For comparison, Earth's own geothermal heat flow, the heat from radioactive decay in the rocky interior, is about 0.09 watts per square metre. Europa's tidal heating is comparable to Earth's own internal heat source, not dramatically more, comparable, enough to maintain a global liquid ocean, enough to drive hydrothermal circulation at the seafloor. The distribution of that tidal heat within Europa's interior is concentrated in the silicate mantle and at the seafloor. The rocky core deforms slightly with each tidal cycle. Friction in the deforming rock generates heat. The heat drives thermal convection in the rocky mantle, the same convection that drives plate tectonics on Earth. At the boundary between the mantle and the ocean, hot material rises and contacts the cold ocean water above it. The chemistry of that contact is the hydrothermal chemistry that Cassini found at Enceladus. The same chemistry that has been driving the most ancient and robust ecosystems on Earth since before complex life appeared. 4 billion years of that process in an ocean with confirmed carbon. The implications depend on one specific question that the Webb observation raised without answering, and that Clipper is designed to address: whether the rock-water chemistry at Europa's seafloor has been producing hydrothermal systems as active and chemically rich as those at Enceladus, and whether those systems have been the site of anything beyond geology, in the dark. With heat from below, with minerals dissolving from the rocky seafloor, with carbon dioxide now confirmed in its ice shell chemistry. The process connecting the seafloor to the surface has been operating continuously through the entire history of complex life on Earth. The question of whether that process has been exploiting its ingredients depends on what happens at the floor of the ocean, and the closest thing in the solar system to a direct answer to that question came not from Europa, but from a smaller, less dramatic moon of Saturn. If this is the kind of content you come back for, subscribe now and share this video. It genuinely helps the channel reach people who are looking for this. Back to Europa. Saturn has a moon called Enceladus. It is 310 miles across. Europa is nearly 2,000. By every measure of scale, Enceladus is the lesser world. Enceladus changed everything. The discovery was not immediate. Cassini's first close flyby of Enceladus in 2005 found anomalies: an unexpected heat signature at the South Pole, a tenuous atmosphere where none was expected, fine particles of water ice in the E-ring of Saturn that seemed to originate from the Moon. The interpretation required multiple flybys and years of analysis. By 2008, the picture was clear. Enceladus was actively erupting from its south polar tiger stripe fractures. The geysers were continuous. The plume was real. Cassini flew through the plume 23 times over 13 years. The chemical inventory built slowly with each pass. Early flybys confirmed water vapor, salt, and simple organic molecules. Later flybys with improved targeting and instrument settings found molecular hydrogen in 2017, the finding that clinched the hydrothermal interpretation. The hydrogen was too abundant to be explained by radiolysis of water ice. It required an ongoing chemical reaction between hot water and rock, serpentinization. The same reaction that feeds the chemotrophic bacteria at alkaline hydrothermal vents on Earth. Cassini had found, by accident, a world where the chemistry most associated with the origin of life was actively running. The 2017 paper by Waite and colleagues in Science was the turning point. It was not a speculative paper, it was a measurement paper. The hydrogen was measured, its quantity was calculated. The serpentinization reaction was identified as the only source consistent with the data. The conclusion was stated simply: Enceladus's ocean is in contact with hot rock. The seafloor is geologically active. The Moon is habitable in the precise technical meaning of that word. It has the conditions necessary to support life of the type found at hydrothermal vents on Earth. The Cassini spacecraft arrived in the Saturnian system in 2004 and spent 13 years there. Early in the mission, it detected something unexpected near Enceladus's south pole: geysers, water vapor, ice particles, gas, erupting from a set of fractures in the south polar ice called the Tiger Stripes, and spraying continuously into space. Cassini flew through these plumes 23 times. It pointed its mass spectrometer directly into the erupting material, the chemical inventory of the Enceladus plume: water vapor, carbon dioxide, methane, molecular hydrogen, silica nanoparticles, complex organic molecules with masses above 200 atomic mass units. Molecular hydrogen and silica nanoparticles appearing together have a specific chemical meaning. On Earth, this combination is the fingerprint of serpentinization, hot seawater reacting with ultramafic rock on the seafloor. When water meets peridotite at high temperature, the minerals react with the water and release molecular hydrogen as a direct byproduct. It is the same reaction that feeds the chemotrophic bacteria at alkaline hydrothermal vents on Earth's seafloor. Bacteria that do not use sunlight, that run entirely on chemical energy from the planet's interior. Cassini found the fingerprints of this process at Enceladus. Hunter Waite's team at the Southwest Research Institute published the finding in Science in 2017. The conclusion: Enceladus has active hydrothermal vents. A moon the size of a small city in Saturn's system is running, right now, this same chemistry that some researchers believe sparked life on Earth 4 billion years ago. If vents exist on Europa's seafloor, the carbon Webb found has been cycling through a living chemistry for billions of years. Europa is a better candidate for sustained hydrothermal activity than Enceladus by almost every physical measure. Its rocky core is larger. The silicate mantle provides more rock-water interface for serpentinization to operate. Tidal heating from Jupiter is more intense than Enceladus experiences from Saturn. The ocean has been running longer. More mass, more energy, more time, more interface. The same physical process confirmed at Enceladus has more favourable conditions at Europa. The specific mechanism that serpentinization operates through is worth understanding in detail because it is the mechanism most directly connected to the origin of life hypothesis that makes Europa scientifically compelling. When water at elevated temperature, around 300 to 400 degrees Celsius, flows through fractured ultramafic rock, the olivine and pyroxene minerals in the rock react with the water. The reaction converts these minerals into serpentine and magnetite, releasing molecular hydrogen as a direct chemical byproduct. The hydrogen is not a trace byproduct. It is produced in substantial quantities wherever the reaction is active. At the alkaline hydrothermal vents on Earth where this reaction occurs, the hydrogen-enriched vent fluids create strong chemical gradients against the surrounding ocean water. Mike Russell at NASA's Jet Propulsion Laboratory and Nick Lane at University College London developed the leading origin of life hypothesis centered on exactly these alkaline vents. In their model, the proton gradient between the alkaline vent fluid and the mildly acidic ocean water outside the vent creates a natural chemiosmotic force, the same thermodynamic driver that powers the biochemistry of every cell on Earth through ATP synthase enzymes. The vent wall itself, made of porous iron-sulfur minerals, concentrates the relevant chemicals and catalyzes reactions similar to those that occur in modern metabolism. The hypothesis is that life originated not in Darwin's warm little pond, but in cool, alkaline, porous hydrothermal vents, where thermodynamic gradients drove chemistry toward the organizational complexity we call biology. If Europa's seafloor has alkaline hydrothermal vents, and the physical evidence strongly implies it does, the Russell-Lane conditions are present. The proton gradient between vent fluid and ocean water would exist. The iron-sulfur minerals would be in the vent walls. The molecular hydrogen from serpentinization would be available as the primary energy source. The carbon dioxide confirmed by Webb would be the carbon source. The 4 ingredients of the Russell-Lane hypothesis, gradient, mineral catalyst, hydrogen donor, carbon acceptor, are all present or strongly implied in Europa's ocean. What serpentinization at Europa's seafloor would produce molecular hydrogen? Silica minerals in the ocean water, heat concentrated at the vent sites, chemical gradients between the hot vent fluid and the surrounding cold ocean, temperature gradients, concentration gradients, pH gradients. These gradients are energy sources. On Earth, chemotrophic microbes use exactly these gradients as their power supply, the same way a turbine uses the gradient between high pressure and low pressure steam. The process does not require sunlight. It does not require surface conditions. It requires hot water, rock, and time. Europa has all 3. Confirmed. The carbon that Webb detected is not just a static molecule sitting in the ice. It is part of a cycle. Ocean water cycles through the seafloor chemistry at the vents. Carbon compounds are dissolved, reduced, processed, released back into the ocean. The ocean water freezes onto the base of the ice shell. The convecting shell carries the carbon upward. The chaos terrain delivers it to the surface. Webb reads it. The entire pathway from the possible vent chemistry on the seafloor to the near-spec signal in Terra Regio is a connected, active system, one driven by Jupiter's gravity at the bottom and readable by a telescope at the top. The question is whether that system has been producing chemistry or biology, and understanding that requires following one more thread: what the models said before Webb looked, and why the Webb finding required those models to be revised. Before Webb observed Europa, the planetary science community had detailed models of its surface chemistry. These were not speculative. They were built from data: Voyager flyby images from 1979, Galileo measurements across 11 close flybys in the late 1990s and early 2000s, Hubble ultraviolet observations accumulated over decades. The models were internally consistent, matched every prior measurement, and made specific predictions. The predictions were wrong in a specific way. Pre-Webb models expected Europa's surface chemistry to be dominated by external inputs processed by Jupiter's radiation. Radiation from the particle belts drives chemistry in the surface ice. Sulfur from Io's volcanic eruptions deposits onto the surface. The models expected these processes to produce chemical signatures distributed broadly across the surface, with older terrain accumulating more of the radiation-processed products over time. The models were built on the assumption that the ice shell sealed things in. Webb showed it seals things out. Sealed things in? The ocean's chemistry stays below. The surface reflects only external processes acting from above. Seals things out. The surface chemistry is what the ocean releases upward. The chaos terrain is a readout of ocean composition, not a record of space weather. This distinction is not minor. It changes the interpretive framework for every chemical measurement ever made of Europa's surface. If the surface reflects the ocean's chemistry in the young, disrupted terrain, then the chaos terrain is a chemical window, not into the sky, but into the ocean below. Webb read through that window from 390 million miles. Clipper will read through the same window from 25 kilometers. The practical consequence of the model revision is significant for Clipper's observation planning. If the surface chemistry in chaos terrain regions reflects internal inputs from the ocean, rather than external inputs from space, then the chaos terrain is a chemical window into the ocean. The specific combination of compounds present at the surface in Terra Regio, measured at the spatial resolution and chemical depth that Clipper's close-range instruments provide, constitutes a sampling of the ocean's chemistry, filtered and modified by transit through the ice and by radiation processing at the surface, but fundamentally connected to the ocean below. Tara Regio is among the highest priority targets in Clipper's flyby plan precisely because Webb identified it as the location where the internal to external chemical signal is clearest. Flyby trajectories are designed to pass over it multiple times at different lighting conditions and at different altitudes in the range around the closest approach of 25 kilometers. Each pass builds a more detailed picture of the chemical character of that specific region, from the ice surface through the near-surface exosphere to whatever is being released into space from that location. The revision also suggests that the older terrain elsewhere on Europa, which shows less of the internal chemistry signal, may be less useful for sampling ocean chemistry. It has been exposed to radiation processing for longer. Whatever internal chemistry arrived there in past geological epochs has been more thoroughly degraded. Tara Regio, young and freshly refreshed from below, is the cleanest window. That is why Webb found the signal there. That is why Clipper will focus its highest sensitivity observations there. There is a secondary implication of the revised model that is worth stating clearly. If the surface chemistry of chaos terrain reflects the ocean's chemistry, then every future discovery of chaos terrain on any icy ocean world becomes scientifically significant. Europa Clipper will map Europa at high resolution across all 49 flybys. It will identify chaos terrain regions we have not yet catalogued. Each one is a potential chemical window. If Maspex finds a biosignature signal above Terra Regio, scientists will immediately prioritize every other chaos terrain region on the flyby schedule and ask whether the same signal appears there too. Confirming the signal in multiple independent locations would be among the strongest possible forms of evidence. But the window may also be open in a more dramatic sense. The question of whether Europa erupts the way Enceladus erupts determines what Clipper will be able to sample and at what level of chemical fidelity. Enceladus erupts. This is not tentative. Cassini photographed the plumes, flew through them 23 times, and analysed their chemistry directly. The eruption is continuous. The plumes are active right now. They have been active throughout the 13 years Cassini spent in the Saturnian system. Europa might erupt. The evidence raised hope. Each attempted confirmation complicated the picture. The Hubble Space Telescope made a candidate detection of plume activity on Europa in 2012. A team led by Lorenz Roth reported elevated hydrogen and oxygen emissions above the southern hemisphere, at a location and intensity consistent with a water vapour plume rising 200 kilometres from the surface. The signal looked like what Hubble had seen at Enceladus before Cassini confirmed the plumes in detail. The team labelled it tentative. Subsequent Hubble passes over the same region produced inconsistent results. The signal appeared in some observations, in others, nothing. A 2016 paper by William Sparks reported ultraviolet absorption features consistent with a plume in some additional Hubble observations, not all. The detections were not reproducible with the consistency the community requires to call something confirmed. The story of the Europa plumes is hint, then inconsistency, then unresolved. Europa may not need to erupt. The ice itself does the work. The convective upwelling model explains the carbon dioxide signal without requiring a single crack in the ice. The ocean delivers chemistry to the base of the shell. The shell convects it upward over hundreds of thousands of years. The chaos terrain is where the delivery reaches the surface. No eruption, no plume. Just the slow, relentless churning of a 15 to 25 mile ice shell, carrying ocean chemistry toward the surface. But eruption changes the calculus completely. If Enceladus-style plumes exist at Europa, they carry unmodified ocean water directly into space. Europa Clipper's Maspex mass spectrometer, flying through a plume at 25 kilometers altitude, samples the ocean water directly. No transit through the ice. No hundreds of thousands of years of radiation processing. no dilution through convective averaging. The ocean water itself in real time entering the instrument's ionization chamber. Cassini did exactly this at Enceladus. That direct sampling gave scientists the most detailed chemical inventory of any ocean beyond Earth. Molecular hydrogen, organic molecules, the hydrothermal fingerprint, all from plume fly-through. If Europa has active plumes and Clipper flies through one, the science return is comparable. If it does not, MASSPEC still measures the near-surface atmosphere above the chaos terrain, the diffuse release of compounds from the convecting ice, the trace gases above Tara Regio. Harder to read, but still readable at MASSPEC's sensitivity. Either way, Clipper is looking for the same thing, what the ocean is made of. Whether the carbon found by Webb is part of a purely geological cycle, or part of something more. That search begins in April 2030, and the instrument that will conduct it is worth understanding before discussing what it will mean to find something. The plume question matters for a specific reason beyond sampling fidelity. Active plumes would tell scientists something about the mechanical state of the ice shell that passive convection alone does not. If Jupiter's tidal force is opening fractures in the ice shell cyclically, as Io's tidal heating opens fractures in that moon's crust to drive its volcanism, those fractures represent pathways for ocean water to travel directly from the ocean to the surface without spending hundreds of thousands of years in the convecting ice. The chemistry in a plume is unmodified ocean water. The chemistry in the convecting ice is ocean water that has been frozen, transported, partially irradiated and partially degraded. Cassini's greatest scientific achievement was not detecting the plumes, it was flying through them. The direct sampling of unmodified ocean water from Enceladus by a mass spectrometer instrument gave scientists the most detailed chemical inventory of any ocean beyond Earth. Molecular hydrogen at a specific concentration that implied serpentinization at a specific temperature, complex organics at specific mass ranges. The data were enough to make quantitative statements about the seafloor chemistry, not just qualitative ones. If Clipper flies through a plume from Europa's ocean during one of its 49 flybys, MASSPEC gets the same opportunity Cassini had at Enceladus. Direct sampling of unmodified ocean water. The science return from a single confirmed plume fly-through would exceed the science return from dozens of flybys over the diffuse atmospheric chemistry above the chaos terrain. This is why confirming or ruling out Europa plumes is itself a major objective of the Clipper mission, not just a secondary finding. Europa Clipper's closest approach altitude of 25 kilometers is itself driven partly by the plume science. If Europa's plumes reach heights comparable to Enceladus's plumes, which extend to 200 kilometers and beyond, a 25-kilometer flyby passes well within the plume column. MASSPEC, operating at 1 part per trillion sensitivity, would sample plume material at concentrations orders of magnitude higher than the diffuse background chemistry of the exosphere. The scientific return from a single confirmed plume fly-through would compress the science timeline dramatically. Months of accumulated flyby data from diffuse atmospheric sampling might be surpassed in scientific value by a single hour of sampling inside an active plume. The Hubble plume candidates, while unconfirmed, appeared concentrated in the southern hemisphere of Europa. The tiger stripe fractures on Enceladus are also near the South Pole. The orbital dynamics that drive tidal stress on icy moons concentrate certain stress patterns near the poles. Clipper's flyby plan includes targeted passes over Europa's southern hemisphere, precisely because the candidate plume locations identified by Hubble are there. If plumes are active and intermittent, the probability of Clipper flying through one during at least one of its 49 flybys is not negligible. The Clipper mission plan includes dedicated plume search observations. UVS will scan the limb of Europa during close approaches, looking for the ultraviolet emission signature that would indicate a plume column above the surface. MISS will look for frost deposits on the surface downwind of any active venting. MASSPEX will maintain a continuous sampling mode during close approaches, capturing whatever is present in the near-surface environment, regardless of whether it looks like a plume column from above or a diffuse release from the convecting ice below. Europa Clipper launched October 14, 2024. Kennedy Space Center, Falcon Heavy. The largest planetary science spacecraft NASA has ever built. With its solar arrays deployed, it spans more than 100 feet. Those arrays are enormous because Jupiter receives 4% of the sunlight that reaches Earth, and 9 science instruments running for years require substantial electrical power from diminished sunlight. It arrives at Jupiter in April 2030. Webb read the surface from 390 million miles. Clipper will smell the ocean from 25 kilometers. Clipper does not orbit Europa directly. The radiation belts around Europa would destroy spacecraft electronics within months if the spacecraft were in continuous orbit there. Instead, Clipper orbits Jupiter, far enough from Europa to survive for years, and makes 49 planned close flybys of the Moon. Each flyby brings it within 25 kilometers of the surface. Each flyby covers a different region, building cumulative coverage of nearly the entire Moon. Tara Regio, the specific region where Webb found the carbon dioxide, is among the targeted areas. The instrument that does the smelling is called MASSPEX, Mass Spectrometer for Planetary Exploration, built by the Southwest Research Institute, the same institution whose Cassini instrument found the hydrothermal fingerprint in the Enceladus plumes. MASSPEX works by drawing in gas molecules from the near-surface environment, ionizing them into charged particles, and then bouncing the ions back and forth inside a device called a reflectron up to 400 times. The time each ion takes to complete its 400 bounce transit depends on its mass. Heavier ions take longer, lighter ions take less time. By measuring the transit time with extreme precision, MASSPEX determines the mass of the molecule. Mass determines identity. Identity reveals composition. Isotopic ratios, the relative proportions of different isotopes of the same element, are readable from mass differences smaller than a single atomic mass unit. Its sensitivity, 1 part per trillion. 1 part per trillion. If you took a single grain of table salt and dissolved it into 500 Olympic swimming pools, the resulting concentration would be roughly 1 part per trillion. MASSPEX would detect it. At that sensitivity, MASSPEX can detect complex organic molecules in the near-surface atmosphere above Tara Regio even after they have been through the full degradation pipeline. Dissolved in the ocean, incorporated into ice, convected upward for hundreds of thousands of years, exposed to Jupiter's radiation at the surface, sublimated into Europa's tenuous exosphere. Each step dilutes and degrades the signal. MASSPEX was calibrated against the expected dilution at each step. MASSPEX can also read isotopic ratios. The ratio of carbon-12 to carbon-13 in biologically processed carbon is different from the ratio in geologically processed carbon. Life preferentially uses the lighter isotope because lighter atoms are fractionally easier to move through enzyme systems. This fractionation signature, the isotopic bias toward carbon-12, survives the radiation processing that destroys intact complex molecules. Isotope ratios do not degrade the way molecular structures do. Clipper's Reason radar instrument will probe the ice shell directly. Radar waves penetrate ice and reflect off boundaries between layers of different density. At Europa, the boundary between the bottom of the ice shell and the top of the liquid ocean will produce a reflection that Reason can detect. This will give scientists the first direct measurement of ice shell thickness in specific locations. Exactly how thick is the ice above Tara Regio? If the shell is thinner there, the convection model is confirmed. If not, the model needs revision, and the revision tells scientists something specific about why the carbon dioxide pattern looks the way it does. 9 instruments total, all active simultaneously during each flyby, all looking at the same location at the same time. The chemical data from mass specs, the surface maps from the imaging spectrometer, the ice thickness from reason, the magnetic field from the magnetometer, the plasma environment from the particle instruments. Every flyby produces a multidimensional data set. The picture builds with each pass, all looking at the same location at the same moment. During a close flyby of Tara Regio, MassSpec samples the chemical composition of the exosphere above the chaos terrain at 1 part per trillion sensitivity. The mapping imaging spectrometer for Europa, MESA, maps the surface composition at spatial resolutions that Webb could not achieve from 390 million miles away. The surface dust analyzer, SUDA, captures individual dust particles released from the surface and analyzes their composition. The Europa ultraviolet spectrograph, UVS, looks for plume signatures in the ultraviolet, the same wavelength range where Hubble saw its candidate plume detections. The ice-penetrating radar, REASON, probes the ice shell thickness directly at the same location MassSpecs is sampling from above. The multi-instrument simultaneity is deliberate. A chemical detection in MassSpec's data from above Tara Regio has a very different scientific weight depending on what MIS found on the surface directly below the sampling point, what REASON measured about the ice shell thickness at that location, and whether UV saw any plume signature at the same time. If MassSpecs finds an isotopically fractionated compound, while REASON simultaneously measures a locally thin ice shell and UVS simultaneously sees a plume, each measurement independently supports and is supported by the others. The accumulation of correlated evidence from independent instruments is what converts a suggestive detection into a scientifically defensible claim. Each of the 49 flybys is planned with this logic. The trajectory, altitude, and timing are chosen to maximize the scientific value of the multi-instrument dataset. Some flybys are high-altitude passes for broad mapping. Some are the closest approaches for sensitive atmospheric sampling. The targeting of Tara Regio is explicit in the flyby plan precisely because Webb established it as the location with the clearest connection between ocean chemistry and surface chemistry. Clipper will read that connection with instruments 3 orders of magnitude more sensitive than anything that has approached Europa before. The trajectory design for Clipper's 49 flybys was not simple to plan. Europa Clipper orbits Jupiter at a distance and period chosen to produce close approaches to Europa at specific times, from specific angles, over specific surface regions. The radiation dose accumulated by the spacecraft increases with every close approach to Europa, since the radiation belts are most intense immediately around the Moon. The mission design balanced the scientific requirement for many close flybys against the engineering constraint that the radiation dose accumulated over all 49 flybys must not exceed what the spacecraft hardware was designed to survive. Every flyby is a budget item in the radiation dose ledger. The closest approaches, the flybys at 25 kilometers, are the most scientifically valuable and the most radiation intensive. They are scheduled strategically, with lower priority observations made during higher altitude passes that accumulate less radiation dose per pass. The flybys over Terra Regio, the confirmed chemical window into the ocean chemistry, are among the highest priority passes in the plan. MassSpecs will be operating at full sensitivity during those passes. The data volume from a 25-kilometer flyby over Tara Regio will be compressed, prioritized, and transmitted back to Earth as efficiently as the telecommunication system allows. The transit time for a signal from Europa to Earth varies with the relative positions of Earth and Jupiter, as both orbit the Sun. At closest approach between Earth and Jupiter, the signal takes about 35 minutes each way, the same travel time as the sunlight that NIRSPEC analysed when it found the carbon dioxide. At greatest separation, the signal takes over an hour. MASSPEC's data collected during a flyby in April 2030 will not reach Earth until well over an hour after the flyby is complete. The science team will be waiting, the data will arrive, and the analysis that follows will determine whether what MASSPEC sampled above Tara Regio is consistent with 4 billion years of geology or 4 billion years of something more. The picture starts being built in April 2030. What it will show depends on what is actually in Europa's ocean, and that question has a realistic answer that does not look like science fiction, but is in some ways more significant. The image most people carry of alien life on Europa is cinematic. Creatures in the dark ocean. Something complex. Something moving. Something that would be recognizable as alive in the way a fish is recognizable as alive. Dismiss that image entirely. The realistic candidate is a microbe, a single-celled organism smaller than a human cell, possibly smaller than a bacterium, running on chemistry instead of sunlight, producing metabolic byproducts instead of offspring visible to the eye, leaving chemical traces instead of fossils. Not dramatic. Not recognizable in any cinematic sense. The most significant life in the solar system may have never once needed a sun. In 1977, the research submersible Alvin descended to 2,500 meters on the East Pacific Rise in the Pacific Ocean. The scientists aboard expected darkness, cold, and biological emptiness. The light existed. The cold existed. The emptiness did not. At 2,500 meters, in conditions where no photosynthesis is possible, in depths below any light from the surface, there was an ecosystem. Giant tube worms over 2 meters long, white crabs, blind shrimp, clams, a food web as dense and productive as any sunlit reef. Nothing in it ran on sunlight. The base of the food chain was chemotrophic bacteria, microbes that oxidize hydrogen sulfide from the hydrothermal vents and use the released energy to fix carbon dioxide into organic molecules, the same carbon fixation that photosynthesis performs, driven by chemistry instead of photons. These bacteria were eaten by organisms that were eaten by organisms higher in the chain. The entire ecosystem was powered by the planet's interior, not the sun. This was not an isolated finding. In the years since 1977, the range of environments where chemotrophic microbial life has been found on Earth has expanded to include cracks in basaltic rock 2 kilometers below the ocean floor, saline lakes with pH above 11, brine channels in Antarctic sea ice at minus 20 degrees Celsius, the cooling water of nuclear reactors, environments where temperature, pressure, pH and chemistry make survival seem impossible by any intuitive standard. The universal requirements for microbial life on Earth, distilled from every environment where it has been found, are 2: a source of chemical energy in any form and liquid water. Everything else is negotiable. This list has been tested by every extreme environment found on Earth in the years since the Alvin discovery. It has not been violated. Chemical energy plus liquid water, sufficient, repeatedly confirmed. Remove either, no life found. The requirement for light, temperature, pH, pressure within specific ranges. All of these have been shown to be negotiable by organisms that have adapted to conditions that would kill any organism familiar to 19th century biology. The 2 requirements stand as a minimum. Europa satisfies both. The chemical energy is available from 2 sources: tidal heating concentrated at the seafloor and the rock-water reaction at the base of the ocean. The liquid water is confirmed by the electromagnetic signature Galileo measured in the late 1990s and by decades of modelling that has constrained the ocean's depth, salinity, and extent. The two necessary conditions are both present. The question is whether the sufficient conditions for origin are met, a question that no current measurement of any world other than Earth can fully answer. The methanogens that astrobiologists consider the most probable candidate type for Europa's ocean are among the most metabolically stripped down organisms on Earth. Their metabolism runs on two molecules, molecular hydrogen and carbon dioxide. The reaction produces methane and water, releasing a small amount of energy that the organism captures to drive its cellular processes. The pathway is so simple, and the energy yield so small, that methanogens operate at the very low end of the metabolic rate spectrum for any living organism. They grow slowly, they reproduce slowly, they consume resources at rates so low they are difficult to measure. They have survived in isolation in Earth's deep subsurface for millions of years. These organisms are not evolutionarily advanced. They are among the most ancient lineages on the tree of life. Their extreme simplicity may not be a limitation, but an advantage in resource-poor environments. An ocean that provides molecular hydrogen from serpentinization and carbon dioxide from the carbon cycle, Webb confirmed would, under this framework, be a suitable environment for methanogen-type life. Not confirmed, suitable. The chemical inputs are present. The liquid medium is present. The energy source is present. Whether the origin step occurred is the unanswered question. The timescale available for that question to resolve itself on Europa is almost incomprehensible. The origin of life on Earth is believed to have occurred within the first 500 million years of the planet's history, possibly faster. Some researchers argue that life appeared within the first 100 million years of Earth, having stable liquid water, based on carbon isotope signatures in ancient rocks and controversial microfossil evidence from 3.7 billion-year-old formations in Greenland. The point is that on Earth, life originated early. It did not take the full 4.5 billion years, it took a small fraction of that. If the origin of life is a chemical process that runs given the right inputs and enough time, and if the inputs in Europa's ocean have been approximately constant for 4 billion years, the timescale available for the origin step on Europa is 8 to 40 times longer than the timescale during which life appears to have originated on Earth. Either it happened early, as it did on Earth, and has been running for billions of years, or the origin step failed despite 4 billion years of opportunity, suggesting that the conditions at Europa are missing some ingredient we have not identified, or that the origin of life requires specific conditions that Europa's ocean lacks despite its apparent suitability. Both conclusions are scientifically important. Both move the field forward. A positive biosignature detection from mass spec says, life originates early when the conditions are right, has been running continuously in Europa's ocean, and the origin step is not the great filter. A null result from mass spec says, the origin step failed in 4 billion years with apparent favourable conditions, suggesting we're missing something essential in our understanding of what those conditions actually require. Neither outcome is a failure for the scientific program. Both outcomes are among the most consequential empirical results in the history of astrobiology. The microbial population that mass specs is designed to detect would not need to be large. The deep-sea chemotrophic ecosystems on Earth produce biomass at rates far below what sunlit ecosystems produce. The total biomass of all chemotrophic organisms in Earth's deep subsurface and deep ocean is estimated at roughly 70 billion tons of carbon, comparable to the total biomass of all surface life on Earth. But this biomass is distributed across a much larger volume, deep crustal environments extending kilometers into the rock. The concentration of living organisms per cubic meter of deep subsurface rock is extraordinarily low. MassPex does not need a dense productive biosphere. It needs the chemical output of any biosphere at all, accumulated over millions of years and concentrated in the compounds the ice shell releases into the exosphere above Terra Regio. Europa satisfies both. The specific microbial group that astrobiologists consider the most probable candidate for Europa's ocean is the methanogens, anaerobic archaea, among the most ancient lineages of life on Earth. They combine molecular hydrogen with carbon dioxide and produce methane as a metabolic byproduct. The reaction is simple. The two reactants, hydrogen from serpentinization and carbon dioxide confirmed by Webb, are both expected or confirmed in Europa's ocean chemistry. The product, methane, is detectable by MassPex at concentrations so low that even a sparse microbial population operating at the slow metabolic rates typical of deep-sea chemotrophic organisms would leave a measurable trace in the compounds the ice shell releases into the atmosphere above Terra Regio, 4 billion years. If methanogens or anything analogous began operating in Europa's ocean at any point in its history and found a viable chemical niche, their metabolic byproducts have been accumulating in the ocean, incorporated into ice, transported upward, and released at the surface for the entire history of complex life on Earth. The chemical record of 4 billion years of possible microbial activity does not disappear. It accumulates. It modifies the isotopic ratios of the carbon compounds in the ice. It alters the relative concentrations of methane, hydrogen, and carbon dioxide in the chemistry that reaches the surface. MassPex is sensitive enough to read that record. The question of what finding that record would mean is larger than the planetary science. It connects to a question that has been sitting unanswered in physics and philosophy since 1950. And the connection is not abstract. It is direct and unsettling. Subscribe and turn on notifications if you want to be here when the Clipper data starts coming in. Share this with someone who should be thinking about this question. Back to the final piece. In 1950, Enrico Fermi sat down to lunch with colleagues at Los Alamos and asked a question that has not been answered since. The galaxy contains 100 billion stars. Many have planets. The universe is 13.8 billion years old. Even travelling at a fraction of the speed of light, a civilization that had a billion-year head start on us could have colonized the entire Milky Way multiple times over. So where is everyone? The Great Filter is the concept that emerged. Something prevents civilizations from becoming visible at galaxy-spanning scale. Something filters them out. The filter could be at the origin of life. It could be at the development of complex cells. It could be at intelligence or technology, or what technology does to civilizations. The filter is either behind us, mostly in the past, or ahead of us, mostly in the future. Finding life on Europa would be the most terrifying good news in human history. Here is the architecture of why. If life arose on Europa, it arose in isolation from Earth. No genetic connection, no shared ancestry, no meteor exchange that could have carried biology from one world to the other across the relevant distances. Different chemistry, different energy source, different environment. If life is in Europa's ocean, it started there from scratch, driven by tidal heating and the carbon chemistry of a rocky seafloor in a lightless ocean. A second independent origin of life anywhere, under any conditions, moves the sample size from 1 to 2. One example tells you life is possible. 2 examples tells you the process runs whenever the inputs are present. Water, chemical energy, carbon chemistry, and time. If the process ran in Europa's ocean, it almost certainly ran in the subsurface oceans of Enceladus, Ganymede, Titan, and the hundreds of billions of ocean worlds that exist around other stars. The galaxy is not empty, it is saturated. A universe saturated with microbial life is a universe where the filter is not at the origin step. Life starts. It starts easily. Whatever filters out civilizations before they become visible operates later, at intelligence, at technology, at something we have not identified yet. And a filter that operates after life begins applies to us as much as to everything that was not visible when Fermi asked his question. The other outcome carries its own weight. If Europa's ocean is sterile, if 4 billion years of confirmed liquid water and confirmed carbon chemistry and confirmed tidal energy has produced nothing biological, then the origin of life is not easy. The step from complex chemistry to self-replicating chemistry is the filter. It happened here, once, improbably. The galaxy may be filled with worlds that have all the ingredients and have never crossed the threshold. We crossed it. We may be nearly alone. Both outcomes are equally significant. Both reshape the framework entirely. The positive detection is wonderful and frightening. The null result is lonely and potentially reassuring about our future. The positive detection is the one that rewrites textbooks and forces the revision of every assumption about life in the universe. It is also the one that makes the great filter argument most urgent and most personal. A universe where life starts easily, where microbial biology arises whenever the conditions are present, is a universe where the silence in the sky is not explained by the rarity of life. It is explained by something that happens after life starts, that something has not happened to us yet, whatever it is. The null result is less dramatic in the moment it is announced. No headlines about life beyond Earth, no press conferences with images of detected organisms, but the null result carries its own weight. It would mean that 4 billion years of confirmed favourable conditions in Europa's ocean produced nothing. That the origin step is the filter, that we are genuinely rare, and if we are genuinely rare, the moral weight of what happens on this planet increases correspondingly. There is no other instance of what we are doing here. No backup copy. No second location where life in its complex intelligent form is also working on the same problems. Neither conclusion is small. The scientific community has been building toward this measurement for decades, from the Galileo magnetic field detection of the ocean in 1997 to the Cassini hydrothermal confirmation at Enceladus in 2017 to the Webb carbon detection in 2023 to the Clipper launch in 2024. Each step has converted a speculative question into a precise empirical one. The precise empirical question is, does the chemistry above Taura Regio carry isotopic or molecular biosignatures? Mass specs will answer it, one flyby at a time, starting in April 2030. The answer will not come in a single announcement. It will accumulate across multiple flybys, multiple data sets, multiple analyses by multiple independent research teams. The history of astrobiology is littered with claims that were initially compelling and later revised. The Martian meteorite ALH 4001 in 1996, the phosphine in Venus's atmosphere in 2020, multiple candidate biosignature detections from Mars that have been alternatively supported and challenged by subsequent measurements. The scientific community has learned from these episodes to require a level of evidence that goes far beyond a single positive detection. Confirming a biosignature from Europa will require the detection of specific compounds at specific concentrations, confirmation of isotopic fractionation ratios inconsistent with abiotic production, absence of any known abiotic process that could produce the same combination of signals, an independent confirmation by at least one other instrument on Clipper. This is not a bar that should seem unreasonably high. The claim that life exists in Europa's ocean would be the most consequential scientific claim ever made. The evidence required for that claim needs to be proportionally extraordinary. MassSpecs is capable of providing that evidence. The 49 flyby dataset, accumulated over 4 years of science operations, is designed to be comprehensive enough to support such a claim or to rule it out definitively. The science team is ready. The community will scrutinize the data with the same rigor that every extraordinary claim deserves. What makes this moment different from any previous point in the search for life beyond Earth is specificity. Previous searches were broad, looking for life in any form at any location in any environment. This search is precise, looking for the isotopic and molecular biosignatures of chemotrophic microbial life in the near-surface chemistry of a confirmed ocean world with confirmed carbon chemistry, using an instrument specifically designed and calibrated for this detection, flying the closest approach trajectory possible within the radiation constraints of the mission. If life exists in Europa's ocean and produces chemical byproducts that reach the surface, MassSpecs is the instrument most likely to find them. The question has never been this specifically posed before. Whatever loneliness we feel gazing at Europa, the question is symmetric. The answer is out there in the ocean, behind the ice, readable by an instrument already in transit. But before Clipper's data arrives, the honest summary of what we actually know requires confronting what the ice is still hiding. What Webb could not tell us. What no telescope can tell us from any distance. Webb found something real. The carbon dioxide detection in Terra Regio is not disputed. 2 teams, 2 analyses, 1 dataset, same result. Published in the same journal issue on the same day. The localization to young chaos terrain, the exclusion of external sources, the consistency with the ocean as the origin. These conclusions are as well established as near-spec data from a single observing campaign can establish them. The finding is solid, and it falls short of what the most important question requires. Carbon dioxide is produced by geological processes, water-dissolving carbonate minerals, tidal heating processing ancient cometary carbon, radiolysis reactions in the ice driven by Jupiter's radiation. Carbon dioxide is a geological molecule, not a biosignature. Webb confirmed a condition. It could not confirm a cause. Webb gave us a signal. The signal does not tell us if anything sent it. NearSpec reads wavelength-specific absorption. It does not read isotope ratios. It cannot determine the proportion of carbon-12 to carbon-13 in the detected carbon dioxide, the specific isotopic signature that biological processing imprints on carbon compounds because enzymes preferentially use the lighter isotope. It cannot read the suite of companion molecules, the specific combination of methane, hydrogen, and isotopically fractionated carbon compounds that together constitute a biological signature rather than a geological one. Remote sensing from 390 million miles returns one data type. What molecule is present and where? Not what made it. Not what isotopic history it carries. MassSpecs reads all of these. Mass with enough precision to distinguish isotopes, compound identity and companion molecular context simultaneously. The instrument was built for exactly the discrimination that Webb cannot perform. The ice shell is still there, 15 to 25 miles of it, still separating the ocean from the surface. The reason radar will measure its thickness from above, it will not cross it. The ocean itself remains inaccessible until a future mission drills through. That mission does not exist yet in any funded form. The engineering challenge of drilling 15 to 25 miles through ice in the Jupiter radiation environment and deploying a sampling instrument into the ocean below is a problem that no current or near-future technology can solve. It is measured in decades of future work, not years, 15 to 25 miles of it. The reason radar will measure its thickness from above during each close flyby. But measuring the thickness of a barrier is not the same as crossing it. The ocean itself remains inaccessible until the future mission drills through. That mission does not exist yet. Drilling through 15 to 25 miles of ice in the radiation environment of Jupiter, deploying a sterilized sampling instrument into the ocean below, and returning data back to Earth is an engineering problem that is measured in decades of future development, not years. It requires technologies that are in early conceptual stages at best. Europa Clipper is the generation before that mission. Its job is to establish, with enough scientific certainty, that a direct ocean access mission is worth the investment. The investment would be among the most expensive and technically demanding in the history of planetary science. The scientific case for making it needs to be overwhelming. Clipper is building that case. If MassSpecs finds isotopically fractionated carbon compounds in the exosphere above Terra Regio, compounds whose carbon-12 to carbon-13 ratio is shifted in the direction that biological processing produces, the scientific pressure for a direct ocean access mission becomes hard to resist. The isotopic signal is not definitive proof. Abiotic processes can also produce isotopic fractionation in specific circumstances, but isotopic fractionation combined with specific companion molecules, methane at concentrations inconsistent with abiotic production, complex organics with structural characteristics associated with biological synthesis, would build a case that the community would find difficult to explain without invoking biology. The honest position at this moment is this: the conditions are confirmed. The mechanism connecting ocean to surface is confirmed. The instrument capable of reading the chemical character of that connection is in transit. What remains unknown is whether the chemistry that has been cycling through that mechanism for 4 billion years is alive. The answer is in the ocean. The ocean is behind the ice. The ice is still doing exactly what it has been doing for 4 billion years, moving the ocean's chemistry toward the surface, one slow convective cycle at a time, waiting for something sensitive enough to read what it carries. The search for life beyond Earth has been conducted with increasingly precise tools since the Viking landers on Mars in 1976. Vikings' biology experiments produced ambiguous results that divided the scientific community for decades. The ambiguity came from the absence of organic molecules in the Martian soil, not from any definitive biological test. Subsequent Mars missions confirmed that organic molecules do exist in Martian soil, just at lower concentrations than Viking's instruments could detect, and in chemical forms that Viking did not look for. The lesson: the instruments must be matched to the environment and the likely form of any biological signal. MassSpecs was designed with this lesson incorporated. It is not a general-purpose chemistry instrument deployed to a world where the form of any biosignature is unknown. It is an instrument with a specific target chemistry, the methanogen metabolic output expected in a Europa-type ocean, designed to operate in the specific environment of Europa's near-surface atmosphere, calibrated against the expected background chemistry of that environment, and sensitive enough to detect the target signal at the concentrations expected after the full dilution pipeline from ocean to ice to surface to exosphere. The mission is not fishing in unknown waters. It is testing a specific hypothesis with a specific instrument in the specific location the hypothesis predicts. Whether the test returns a positive or a null result, the science is not over. Clipper is the definitive test of what can be reached from above the ice. The next mission, if it comes, goes through the ice, and when it arrives in the ocean, it will be carrying the weight of everything confirmed before it. The liquid water, the carbon chemistry, the hydrothermal energy, the 4 billion years of continuous operation. The ocean will be there. The question of what is in it will finally have an instrument inside it. Clipper is the generation before that mission. Its job is to make the scientific case that a direct ocean access mission is obviously necessary. It does that by building, flyby by flyby, a chemical map of what crosses the ice, what the convecting shell releases into the surface atmosphere above the chaos terrain, what any plumes carry into space, what the isotopic ratios of the detected compounds say about whether the chemistry is geological or biological. If mass specs find something in the atmosphere above Tara Regio that is consistent with biological processing and inconsistent with abiotic chemistry, the pressure to fund a direct ocean access mission becomes scientifically irresistible. If it finds nothing, the question of whether the ocean is too dilute for surface detection or genuinely sterile remains open. The ice shell has been closed for 4 billion years. Webb found one crack in the chemistry. That crack is real. What the ice is still hiding is whether the chemistry that passed through it has a living source. The answer exists somewhere in the ocean. Clipper carries the instrument sensitive enough to look for the isotopic fingerprints of that answer in what the ice releases. Everything confirmed so far has brought us to this moment. Carbon present, ocean real, energy confirmed, mechanism active, instrument in transit. The only thing between the question and the answer is 15 to 25 miles of ice and 6 years of flight time. Something is coming through the ice. That is what the data says, not a model, not a theoretical prediction, a measurement. Carbon dioxide, concentrated in Tara Regio, sourced from the ocean below. 2 independent teams, same result. The finding holds. The ice shell has been closed for 4 billion years. It has been moving chemistry from the ocean to the surface for that entire time, through convection, through chaos terrain formation, through whatever plume activity may or may not exist. Webb read the chemical output of that process from 390 million miles and found that the ocean is not sealed. It speaks through the ice, in carbon dioxide, through the chaos terrain. From behind 15 miles of frozen, slowly churning ice that has been running this cycle since before complex life existed on Earth. What we do not know is whether anything in that ocean put the carbon there on purpose, whether biology has been running in that dark water through the billions of years that life on Earth was building, from the first self-replicating molecule to everything that walks, flies, thinks, and asks questions about other oceans. That question has a spacecraft travelling toward it right now at 34,000 miles per hour. Europa Clipper reaches Jupiter in April 2030. Mass specs will read the chemistry above Tara Regio. The isotopic ratios will say something, the companion molecules will say something, and the accumulation of 49 flybys, each adding another layer to the chemical picture, will eventually narrow the range of possible answers to one. Something is coming through the ice. That is what the data says. Carbon dioxide confirmed in Tara Regio, sourced from the ocean below. 2 teams, 2 analyses, 1 result. The ice shell is not a wall. It has been moving ocean chemistry toward the surface for 4 billion years, one slow convective cycle at a time. Webb read the chemical output of that process from 390 million miles. The signal is real. The source is the ocean. The ice is the mechanism. The question has been building for decades. Galileo confirmed the ocean in 1997. Cassini confirmed hydrothermal vents at Enceladus in 2017 and showed that ocean worlds run the chemistry most associated with the origin of life. Webb confirmed carbon in Europa's ocean chemistry in 2023. Clipper launched in 2024. Each step has converted a philosophical question into a measurable one. The measurement is now in progress, one flyby at a time, through a spacecraft already moving through space at 34,000 miles per hour toward a moon with an ocean that has been waiting for this question to be asked precisely and seriously for 4 billion years. If you want to be here when those answers come in, subscribe. Share this with someone who should be asking this question. That person is everywhere, and the channel reaches them through you. The ice is still there.